welcome you all to Principles of Organic Synthesis. At present, we study the aliphatic carbon nitrogen bond formation. So far, we had 2 lectures in this topic. In this lecture, we will study the reactions of nucleophilic nitrogen with electrophilic carbon. Then the second part will focus on the reactions of electrophilic nitrogen with nucleophilic carbon systems. As you can see in this slide, the reaction of vinyl phosphonium chloride with aldehyde has been shown, with imide followed by reaction with aldehyde and hydrolysis gives allylamine as a product. There are several methods available for the synthesis of allylamine. This is one of the efficient route. If you have vinyl phosphonium salt, you can try to react with imide, and if you react with imide with base, you will be able to generate this anion, which can now undergo addition with this double bond to give this ylide. Once you form this ylide, which can readily react with aldehyde, as you can see here, this can undergo addition here, then this can come here, then you will be able to form this betaine intermediate, which can convert into this allylic derivative, where generate the phosphonium oxide as the byproduct. Once you form this one, when you do the hydrolysis, you will be able to generate this allylic amine as the product. So, if you look at this reaction, it involves 3 steps. First, the base deprotonates this acidic proton, and you will be able to generate this anion. Once you generate the anion, which undergoes addition with this double bond, which acts as the electrophile, it is a nucleophile, undergoes addition reaction to give this phosphonium, this ylide. Once you form the ylide, then it undergoes 2+2 cycloaddition to give this betaine. That betaine can convert into this allyl derivative. And once we have this one, when you do the hydrolysis, you will be able to generate allylamine as the product. If you look at this reaction, it involves the combination of Cabriel and Wittig reactions. In this way, if you have vinyl phosphonium bromide or any salt, which can be readily reacted with imide, the presence of base to give this ylide, that ylide can be further reacted with aldehyde to give this allyl derivative. Once we have this allyl derivative, which can be hydrolyzed to give the allylamine as a product. Here the reaction of alpha bromo vinyl acetate with amine, the presence of base is shown. You can readily undergo reaction to give this aziridine as a product. If we look at here, in this reaction, the amine undergoes conjugate addition. As you can see here, this acts as a nucleophile, this undergoes this electrophile, it undergoes conjugate addition, 1,4 addition. Once then you will be able to generate this salt. The salt in the presence of base, you can deprotonate, then you will be able to get this amine derivative. This can readily convert into this intermediate. Once you form this one, now the amine intramolecularly react with this bromine, as you can via SN2 pathway, then you will be able to generate this aziridine salt. Once you form this salt, this can lose HBr, since you carry out the reaction in the presence of base, then you will be able to get this activated aziridine. So, this is one of the effective route. If you have alpha bromoacrylate, this can be readily reacted with amine, the presence of base, to give aziridine as a product. In this way, you will be able to generate activated aziridine as the product. So, as first it undergoes the 1,4 addition, then followed by intramolecular cyclization by SN2 pathway to give this aziridine salt. Once you form this salt in the presence of base, it can be converted into aziridine as a product. The reactions of ammonia with the nitrile is shown. The first example involves, if you remember earlier, you have this electrophilic nature, this carbon. Once we have the ammonia, it can readily undergo addition reaction. You will be able to form This can convert into so if you have ammonia, that ammonia can readily undergo addition reaction with your carbon triple bond nitrogen of nitrile to give amidine as a product. On the other hand, if you use cyanamide as the substrate, and if you react cyanamide with ammonia, then you will be able to make quinidine as the product, as we have seen. So, this can readily transform into this quinidine as a product. Therefore, if you have ammonia, this can be readily added to nitrile to give the corresponding addition product. If you have simple nitrile, alkyl nitrile, then you will be able to form the amidine. On the other hand, if you have the cyanamide, then you will be able to form quinidine as a product. The next example involves the reaction of methylamine with this isocyanate salt in water medium, and here, as we have seen, it can readily undergo addition with this electrophilic this carbon, then you will be able to form methyl urea as the product. On the other hand, if you use this hydrazine, as here this also can readily undergo addition reaction, then you will be able to form semi-carbazide as the product. If you look at all the reactions, you make a carbon nitrogen bond. Basically, you add a nitrogen nucleophile to electrophilic carbon, then you make a carbon nitrogen bond. And here also you make, when you take the hydrazine as the nucleophile, which can readily undergo addition with this isocyanate salt to give semi-carbazide as the product. You can also try to add, for example, in this case, the reaction of ammonia with methyl thioisocyanate is shown, which can readily undergo reaction, and then you will be able to form methyl thiourea as the product. So, you can write like this: when you do the reaction, you will be able to form methyl thiourea as the product. The next one, the reaction of amine with thioisocyanate is shown here, and as just we have seen, and it can undergo reaction in this case, and you will be able to form the disubstituted thiourea. This, when you react with mercury oxide, you will be able to form the carbodiamide as a product. This is very important compound which we use for the coupling reactions. For example, if you have carboxylic acid and amine, you can couple them together in the presence of the carbodiamide. This we call it as a coupling reagent. Then it can take water, you will be able to form and this will be converted into urea. Basically, it is a dehydrating agent. If you have the carbodiamide, it can readily, if you have the, for example, carboxylic acid, amine, you can make amide. On the other hand, if you have the carboxylic acid, if you have alcohol, you can make ester, and basically you can remove water, it will be converted into urea derivative. We will study the application of this reagent, coupling reagent, in the synthesis of peptide later part. Here the reaction of ammonia with variety of unsaturated carbon systems are shown, and if you look at the reaction of carboxylic benzoic acid with ammonia, you will be able to form this benzamide as the product. by removal of water. Generally, the reaction of amine with aliphatic carboxylic acid is very difficult, it forms salt. However, you can try to make amide with aryl carboxylic acid. The best way is just as we have seen, if you have carboxylic acid, you can readily convert into the corresponding acid chloride, then you can try to react with ammonia, then you can generate the amide as a product. Instead of reacting with carboxylic acid ammonia to make amide, you can convert into acid chloride. Suppose if you have the carboxylic acid, you can react with oxalyl chloride. So, you can convert into the corresponding acid chloride. Once you have acid chloride, then you can readily react with amine. Here the reaction of ammonia is shown, and it can undergo substitution reaction. You will be able to get this amide as a product, where you generate HCl as a byproduct. It is a very simple addition reaction. So, this can, when you do the workup with bicarbonate, it will be converted into amide. HCl will be removed by the base workup. In place of acid chloride, you can also use acid anhydride. This also can readily undergo reaction to give amide as a product, where you generate acid as a byproduct. For in this case, for example, this salt, now you will have this salt can remove this proton, then you will be able to form amide plus carboxylic acid as a byproduct. So, if you use acid anhydride as a substrate, it can also readily undergo reaction with your amine or ammonia, in this case here ammonia. So, you will be able to form the amide as a product, where you generate one equivalent of carboxylic acid as a byproduct. This is another example, as we have seen, this also similar to this substrate anhydride. As we have seen here, if you have ammonia, it can undergo addition reaction with this carbonyl group. Which can convert into intramolecular proton transfer can give the carboxylic acid. Once you form this one, then since this is aryl carboxylic acid, it can undergo intramolecular addition with this carbonyl group, and you will be able to form so this can convert into this can now lose water molecule, then you will be able to form this imide as the product. Therefore, whenever you have the amine or ammonia that can readily undergo addition reaction with this unsaturated carbon system, like if you have the acid chloride, acid anhydride or aryl carboxylic acid, they can be readily converted into the corresponding amide as the product. In addition to ammonia, you can also add other nitrogen nucleophiles. In this case, for example, if you look at here, you have the acid chloride. The reaction of this acid chloride with the hydrogen has been shown, can react as just we have seen just now. You can get this derivative. Once you form this one, now it can undergo further reaction. Now you have the NH2, here you have the amide nitrogen, but among this is nucleophilic enough. This can further react with this acid chloride, and you can convert into corresponding this compound. And if you look at here, the reaction of acid chloride with sodium azide is shown, and you can make acyl azide as a product. This is a precursor for the Curtius rearrangement, all of you know very well. And if you have acyl azide, write like this. Once we have this one, so this can now when you heat, this can come here, this can lose N2, then you will be able to form isocyanate as the intermediate. Once you form this isocyanate, just we have seen, you can try to readily react with a variety of nucleophile addition reactions. You can end up with diverse scaffolds. So, this is the precursor, as you can see here, for the Curtius rearrangement. If you have this acyl azide, when you heat it, it can convert into isocyanate that can be further reacted with variety of nucleophile for the formation of different scaffolds. The next example involves the reaction of this ester with hydroxylamine. When you react, as we have seen, when you react with the hydroxylamine, you can lose what alcohol in this case, since you carry out the reaction with ethyl ester. So, you can end up with this compound which can tautomerize to the hydroxyamic acid, and which we can, when you do the hydrolysis, you will be able to form carboxylic acid and hydroxylamine. If you look at here, what you do is generate a carbon nitrogen bond, a new carbon nitrogen bond between this carbon, the nitrogen of the hydroxylamine, you can make a carbon nitrogen bond, and this compound, as is shown here, hydroxyamic acids give this deeply colored complexes, the iron 3 salts, and this provides a method for the detecting the ester group in qualitative analysis. When you have this hydroxyamic acid, when you react with iron 3 salt, you form a complex. So, this method is used in qualitative analysis to find out whether your system has ester or not. So, when you take this hydroxyamic acid with iron 3 salt, you will be able to form this iron 3 complex, which is, as you see, it gives, this is a deeply colored complex, and this analysis is used to find out the ester group in qualitative analysis. So far we have studied the reaction of nucleophilic amine to electrophilic carbons. whatever we have seen, all the examples involve a nucleophilic amine which undergo readily reaction with electrophilic carbon atoms, you make a carbon nitrogen bond. All the examples involve the reactions of nucleophilic amine to electrophilic carbon systems. Now onwards we are going to look at it, the reactions of electrophilic nitrogen with nucleophilic carbon systems. And this example, look at here, the reaction of HNO2 with this ketone is shown, and you can give this oxime as the product. If you look at the mechanism, when you take this HNO2 in the presence of acid, in acid medium, you can convert into, you can protonate the OH group. As you can see here, you can do the protonation, then you will form this intermediate. Once you form this one, now you have the lone pair, then you can lose water molecule and you can generate the NO plus, this nitrosonium ion. So, when you have the HNO2 in acidic medium, you will be able to generate NO plus, which is electrophile. Already we have seen, if you have ketone in acidic medium, it can exist in enol form. So, once we have the enol now in acidic medium, so this can now act as a nucleophile which can undergo addition reaction as shown here. Once you form the enol, now it can undergo addition reaction with this nitrosonium ion. So, this acts as a nucleophile. This can be formed in acidic medium from the ketone, and once you form this enol, which can undergo addition reaction, then you will be able to form this intermediate. This can lose proton, then you can make this derivative which can convert into oxime as shown here. Therefore, if you have HNO2 in acidic medium can be readily reacted with the enols, you can get the addition product. What you do here, you make a new carbon nitrogen bond between this carbon and the nitrogen of this nitrosonium ion, you make a new carbon nitrogen bond. So, in this reaction, as I mentioned just now, this acts as electrophile, this acts as nucleophile. Some more examples given in this slide. If you look at this 1,3 dicarbonyl compound, when you react with NaNO2 in acidic medium, you will be able to form this oxime. As just we have seen, this also 1,3 dicarbonyl compound in acidic medium can exist, as you can see here, as a enol. Once you have the enol which can readily undergo reaction, if you have this can readily undergo reaction, to give this oxime as a product. The next example involves the reaction of nitromethane. The reaction of nitromethane shown with this nitrosonium ion. As all of you know, this also in acidic medium can exist like this. Once you form this one now, this can undergo addition reaction and you will be able to form this intermediate. Once you form this one, this can isomerize, it can convert into this methyl nitrolic acid as a product. This example, as we have seen, this also can convert into enol. Once you form the enol, as just we have seen, it can also readily undergo addition reaction, then you will be able to form this oxime as the product. And this also similar to this 1,3 dicarbonyl compound, acetylacetone. This also can in acidic medium exists as enol. This enol, whatever you generate, it can undergo addition reaction. then you will be able to form this oxime as the product. So, if you look at all these reactions involve enol as the nucleophile. You have to carry out the reaction in acidic medium, so that the addition reaction can be efficiently carried out. The next example involves, as just we have seen, the reaction of ethyl acetoacetate with the NaNO2 in acetic acid, and it can readily undergo a reaction where NO is the electrophile, this acts as a nucleophile, and once if we have this oxime can be readily reduced using zinc in acetic acid, and you can get this amino derivative. Once you form this amino derivative, which can be readily reacted with another molecule of ethyl acetoacetate, then in this way you will be able to form the tetrasubstituted pyrrolidine as a product. This is one of the effective synthetic route to construct a highly substituted pyrrole. If you look at here, this reaction, first you convert this to this amine derivative. Once you form this one, now this can, when you react, it can make condensation with this carbonyl group, followed by then condensation of this carbon with this one, then you will be able to form the tetrasubstituted pyrrole as the product. The next one, again, this is oxime. Oxime also can be, if you have acidic medium, you can try to do hydrolysis, you will be able to form the diketone. For example, if you have this ketone and you can try to react, then you will be able to form this oxime as the product, ketoxime. Once you form this one, when you do hydrolysis, you can introduce a carbonyl group. So, this is one of the approach. If you want to introduce a carbonyl group in this carbon atom, you can try to react with the nitrosonium ion, then you can make the oxime, and once if you do the hydrolysis, then you will be able to end up with a carbonyl group. So, this here an example shown, you can try to readily make this diketone from this ethyl methyl ketone as a starting material. When you react with the nitrosonium ion in acidic medium, you can get this oxime that can be readily hydrolyzed to give this diketone as the product. So far, we have seen some examples where you use a nitrosonium ion as the electrophile. Now, we are going to look at the use of nitronium ion as electrophile. An example shown here, when you have this benzyl nitrile, this can readily undergo reaction with this nitro compound in the presence of base. You can get this nitro compound after hydrolysis. It involves two steps. First, when you react with base can deprotonate this acidic proton, then you will be able to form which can be stabilized by the aryl ring as well as the nitrile group. Once you form this anion, which can now readily undergo addition reaction with this nitro group as shown, then you will be able to get this salt. Once you form this one, now this can lose methoxy group, then you can get this nitro derivative. Once you form this one, this can be further converted into carboxylic acid, and when you do the decarboxylation, then you can end up with this benzyl nitro derivative. So, if you have the benzyl nitrile compound, you can try to replace the nitrile group with the nitro group as shown. As all of you know very well, already we have studied the hydrolysis of nitrile. If you have nitrile group, acidic medium, you can try to readily convert into carboxylic acid. Once you form this one, now water can undergo addition reaction you will be able to form this can convert into so this can further react with another molecule of water. You will form this salt. Once you form this salt, this can now it can be converted into carboxylic acid. Therefore, nitrile in acidic medium can be readily converted into the carboxylic acid. Once you have the carboxylic acid, already we have seen when you heat it, since you have the electron withdrawing group, nitro group can be readily converted into the corresponding nitro compound by decarboxylation. When you heat it, it can lose carbon dioxide to give this benzyl nitro derivative as the product. Here the reaction of 2,4-dinitrotoluene with this substrate is shown. As you can see here in the presence of base, you can deprotonate the benzylic proton. You can deprotonate. So, you can generate the carbon ion which can be stabilized by the nitro group present in the aromatic ring. Once we have this one, this can readily act as a nucleophile. It can undergo addition reaction with this nitroso compound. As you can see here, this can undergo addition reaction. You will be able to form this hydroxylamine derivative. Once you form this one, now this can lose water molecule as shown here. Then you will be able to form the imine as the product. Once you form the imine, and this can be readily hydrolyzed in acidic conditions, then you will be able to form aldehyde as the product. And so as you can see here, therefore, if you have toluene which is substituted with electron withdrawing group like nitro group is acidic enough that proton can be easily removed by base. The carbon ion now can readily undergo addition reaction with nitrosonium derivative as shown here. Once it can undergo addition reaction followed by dehydration, you will be able to form the Schiff base. Once you form the imine, that imine can readily undergo hydrolysis under acidic conditions, then you will be able to form aldehyde product. This is one of the way, if you have this kind of substrate, it can be converted into aldehyde as shown here. And first what you do here, you react with the base and you generate the anion. Once you form this one, this undergoes addition with this nitroso compound. That addition product gives this hydroxylamine derivative that readily loses water molecule to give this imine as the product. That imine under acidic conditions undergoes hydrolysis to give this aldehyde as the product. So far we have seen several reactions where we have the first part we have seen the reactions of nucleophilic amine with the electrophilic carbons. The second part we have seen the reactions of nucleophilic carbon, particularly enol or carbon ion to the electrophilic nitrogens like nitroso or nitro compounds. Now, let us look at amino acids, peptides and proteins. All of you know very well, peptides and proteins are important components of cells that carry out important biological functions. Peptides are smaller than proteins. Proteins and peptides are very similar by being made up of chains of amino acids that are held together by peptide bonds. Here the structure of a peptide shown, and you can see here amide bond, this between the carboxylic acid and amino group of amino acid. And this is called C-terminal amino acid, this is N-terminal amino acid. Now, let us look at the synthesis of alpha amino acids. As you can see here, if you have the carboxylic acid, you can do halogenation of the alpha carbon atom using, as an example shown here, if you use PBr3 and in the presence of bromine, you can do the bromination of the alpha carbon atom. Once if you have the alpha bromo carboxylic acid, when you react with ammonia, and you will be able to form the alpha amino carboxylic acid. The mechanism of this reaction shown here. As you can see here, this undergoes substitution reaction, and you will be able to form this salt. Once you form this salt, which can undergo addition reaction with this carbonyl group as is shown here, then you will be able to form this can lose then you get this acyl bromide. Once if you have this one, now this can exist in the form of enol. Once you have the enol, it can readily undergo reaction further with bromine as shown here. So, then you will be able to form this alpha bromo acyl bromide. Once you form this one, when you do the hydrolysis, then you will be able to get the alpha bromo carboxylic acid as a product. This is one of the method where you can try to carry out alpha halogenation of carboxylic acid using, for example, in this reaction, the reaction of bromine in the presence of PBr3 has been carried out. In this way, you can introduce the bromine at the alpha carbon atom. Once if you form this alpha bromo carboxylic acid, that can be readily reacted with ammonia, and you can produce the alpha amino acid as a product. Here are some examples are shown. Instead of PBr3, they have used here PCl3, the bromine. So, as we have seen, you can also using PCl3, you can try to form this alpha bromo phenylacetic acid as the product. Once you form this one, as just we have seen, you can react with ammonia. So, by SN2 pathway, then you can make this amino acid as the product, but here the reaction of cyclohexane carboxylic acid is shown with the PCl3 in the presence of chlorine. You can also, as just we have seen, you can introduce chlorine at the alpha carbon atom as just we have seen. And the another approach is shown here, already we have seen Strecker amino acid synthesis. When you have the aldehyde can be readily reacted with amine. By condensation, you will be able to form imine. Once you form the imine, and this can readily undergo addition reaction with one-to-addition reaction, then you will be able to form this alpha amino nitrile as the product. Once you have this one, this can be readily converted into carboxylic acid. Just we have seen, if you have the nitrile group, by acid hydrolysis you can convert into carboxylic acid. So, in this way, if you have aldehyde and amine, and this can be readily condensed to give the imine, that imine can be reacted with the nitrile, and you will be able to form the alpha amino nitrile derivative. This can be further hydrolyzed to carboxylic acid. This is another approach to make the alpha amino acid as a product. Here are another example shown. If you have the ketone can be readily reacted with ammonium carbonate to give imine as shown here. That imine can be reacted with this now cyanide ion, as it can undergo addition reaction. You can get this nitrile derivative. Once if you have this one, this can undergo addition reaction with the carbon dioxide, and proton transfer you will be able to get this compound which can undergo intramolecular cyclization to give this oxoniamine intermediate. Once you have this one, this can convert into this by proton transfer. You can have this isocyanide derivative which can undergo intramolecular addition reaction as shown here. Then in this way you will be able to form this hydrant ion. Once you form this one, when you do the hydrolysis, you will be able to convert into alpha amino acids. So, this is also one of the effective synthetic routes. Therefore, if you have the ketone, this ketone can be readily reacted with ammonium carbonate in the presence of cyanide ion to give hydrant ion that can be further converted into alpha amino acid by hydrolysis. Here some examples are shown. If you look at this ketone, can be readily converted into this derivative. Once if you have this one, when you do the hydrolysis, you will be able to form the corresponding amino acid as a product. And similarly, another example is showing the reaction of this ketone with ammonium carbonate and cyanide ion. This also can be converted into this. This can be further hydrolyzed to the corresponding amino acid derivative. Here the synthesis of peptide are shown. This to condensation of this amino acid. If you look at amino acid, you have the two functional group. One is amino group, another one is carboxylic acid group, and you have to protect one of the functional group. For example, in this case, if you want to react the carboxylic acid, you have to protect the amino group, and so that selectively you can try to react the acid group. And similarly, the another amino acid, you have to protect the carboxylic acid. So now you have the amino group and free carboxylic acid from this amino acid. This two amino acid can be coupled together using coupling reagent. You will be able to form a carbon nitrogen bond, amide bond. So, here some of the common coupling reagents are shown. These are the common carbodiamides used for the coupling of amines and carboxylic acid to make the amide bond. And here some of the examples are shown, and this sometimes this optically active amino acids undergoes racemization. To minimize the racemization, these are the additives are added during the peptide synthesis. Here some of the examples shown for the protecting of the carboxylic acid groups. And if you, for example, if you have the carboxylic acid, you can protect as convert into ester. Here you can convert into methyl ester or benzyl ester or tertiary butyl ester. This production can be carried out. For example, if you want to make the tertiary butyl ester, what you can do here, you can take the carboxylic acid, react with isobutene, the presence of acid medium, then you will be able to form this tertiary butyl ester. As all of you know very well, when you take this isobutene and react with carboxylic acid acid medium, first what happens, it acts as a nucleophile, undergoes addition reaction with this proton, then you will be able to form a tertiary carbocation. This is the electrophile. Once you form this one, now your acid can you will be able to form this ester as the product. So, after the reaction, what you can do, you can also try to deproduct the ester using acidic medium as shown here, the mechanism shown. In this way, you will be able to regenerate the carboxylic acid. So, just we have seen how you can product the carboxylic functional group of amino acid. You can convert into ester, and so after the reaction, you can do hydrolysis, you get back your carboxylic acid. In case of amino group, These are the common protecting group we use for the production of amino group. Here the tertiary butoxy carbonyl group, you can, the unhydrated is available. So you can react with amine, you can react So in this way you can try to protect this amino group. The other common protecting group is this one, carbobenzoxy protecting group. You can also use this one, fluoronyl oxycarbonyl as a protecting group. This is a common protecting group used for the production of amino group in peptide synthesis. An example shown here. So as you can see here, this is commercially available. When you react with amine, the presence of base, you will be able to form, you can, this N protected derivative, as you can see here. Once you form this one, and this, now after the reaction, what you can do when you react with the base, and this proton is acidic enough, now you can deprotonate, and then in this way you will be able to cleave, deproduct this protecting group, and you can get back your amino group. So these are the common protecting group used for the production of amino group in the peptide synthesis. Now let us see one example for the construction of tripeptide. Here the N protected, this glycine has been reacted with this alanine tetrabutyl ester. As you can see, you have the free NH2 group in the case of this alanine part. In the case of glycine, you have the free carboxylic acid. You can couple together using the DCC as the coupling agent. You can make a amide bond between this carbonyl group of this glycine, carboxylic acid, as well as the amino group of alanine. You can make the peptide bond. Once you form this one, as just we have seen, it can act as a base. You can deproduct this proton. You will be able to form this dipeptide. Once you form the dipeptide, you have the free NH2. The another one has the free carboxylic acid. This is derived from phenylalanine. Now again you can make amide bond between this carboxylic acid group, carbonyl group, and this amino group using DCC once again, and then you can make this tripeptide. Once the reaction is completed, as we have seen, you can remove this protecting group using this base. You will be able to get this tripeptide, and this ester group can be easily cleaved using the acid as the catalyst. So in this case, that DCC is converted into corresponding urea. So this is where the synthesis of peptide is carried out. Since amino acid has two functional groups, one is amino group, another was the carboxylic acid group. You have to decide which one you want to react. When you want, you have to protect the other one. In this way, you will be able to carry out the peptide synthesis. Here, the role of DCC and N-hydroxysuccinamide in peptide synthesis shown. The DCC first undergoes reaction with this carboxylic acid, then you will form this O-acyl urea intermediate. It is a good leaving group. Once you have this one, now this can readily react with this N-hydroxysuccinamide to give this urea. This derivative, once you have this derivative, which can be readily now reacted with the amine, as you can see, it can undergo a readily reaction. Then you will be able to generate this as well as this amide as the product. This is converted into dicyclohexyl urea as the product. In summary, today we have seen the first part, we have seen the synthesis of allylamine, aziridines, and the reactions of amines with unsaturated carbon systems. If you look at all these reactions involve amine as a nucleophile, they can readily undergo addition reactions with carbon systems to give carbon nitrogen bond. Then we have seen the second part, the reactions of electrophilic nitrogen with nucleophilic carbon atoms. We have seen particular the reactions of nitrosonium ion and NO2 plus, and so we have seen some examples. Then we have seen the synthesis of amino acids and peptides. With this we conclude this lecture. Thank you very much.